Vanessa? Sorry?
Sorry about that.
Diego? We're looking at lines and angles.
Where was that?
She has a question. She wanted to ask something about the homework.
This one's over, we can go.
Okay, yeah, sorry, go ahead.
Okay, this question, they're asking for the complement of that angle, 89-degree angle. The complement is going to be the angle that you add to that one to get 90. Another way of saying that is do a subtraction problem. So take 90, subtract 89, and you will have a mystical answer of 1 degree. That's the complement of 89 degrees. Because the two of them have to add up to 90. That's the idea. And the others, 8.1.
Yeah, where was I when you handed that homework out? Because I don't have it.
Louis, there's no way of telling that. I will leave you with that thought. I'm sure it was wonderful, wherever it was. Okay.
I was
Any others?
but not even 45.
45. Okay, it says the measure is given. Find the measure of the supplement, 37.4 degrees. Now the supplement is going to be the angle, if you added it to that one, 37.4, get 180. Or another way of saying it is do a subtraction problem. This is a decimal subtraction, so you can put a 0 there. And of course, you have to borrow to get that thing to work. So you go way over here to borrow. That goes to a 7, this is a 9, this is a 10. Standard decimal subtraction. This gives you a 6 here, a 2 there. 7 take away 3 will give you a 4. So there it is. There's your supplement, 142.6 degrees.
70 room.
Okay. got a straight line with a couple parallels crossing it, and it gives you the usual 8-angle thing. They call this A, B, C, 125 degrees, and over here, you have G, E, F, and G. So they want you to find the rest of the angles, just like we did in class yesterday. Okay, these two angles, B and 125, because they're at an intersection, are called vertical angles. And we just accepted without real any proof that vertical angles are equal. So this is 125 also. Now that A up there is going to be the supplement of 125. Why? Because the two of them add up to 180. Straight line is 180. So if you subtracted 125 from 180, again borrowing and so forth, find out that that's 55. Now these two are vertical angles because they're opposite each other in an intersection, so this is 55. So we've got all four of those in that one intersection done. Now the other intersection is exactly the same. You know, it's a carbon copy. But technically you use these things called alternate interior, alternate exterior to figure that out. So let's look at this one right here. This is this A we now know is 55. The alternate interior angle for it, the corresponding angle for it is this one over here. Those are on different sides of the parallel line. One's inside, one's outside, but it's on the same side of the transversal. So this is also 55. And once you've got that to be 55, then the same thing starts happening all over again. This is 55 over here. This is the supplement of 55, which is 125, and likewise, this is 125. So these are two identical intersections in terms of the angles. So it uses all those definitions we had yesterday. Anything else?
41?
41. Okay.
Was that, well, that's one of the questions.
It's okay? Okay. So number 41 is 80 degrees, and the question is, find the measure of the supplement. Okay, once again, you subtract that from 180, and that gives you 100 degrees, so that's the supplement. It's just fancy words that
I'm
math
sorry.
invents.
I'm sorry, I misunderstood. I meant 51, not 41.
Okay.
Sorry. Thank
That's
you.
okay, I do that all the time anyway. All right, it says, can two complementary angles both be acute? Wait a minute, I gotta get things spelled right here, Steve. There we go. Two complementary angles both be acute. Okay, what does acute mean? It means it's awfully cute. What does it mean? It means that it's between 0 and 90. Exactly. It's not 90. 90 is a right angle. Okay, it's not called acute, it's right. But the acute angles are both, can you have two angles that are complements of each other, which means they add to 90, and they are both less than 90? Sure, of course. In fact, that's always the case. Complements are both acute, always, no matter how you draw them. This is a right angle here, which is indicated with a little square like that. This is 90 degrees from here to here, according to the ancients. Okay, any complements are going to be both acute. So here we go, let's just do that one. And we could do this one, doesn't matter. These two, this and this, add up to 90, and they're both acute angles because they're less than 90. Likewise here, you can go here and here, they add up to 90 also. So any two complementary angles have to be acute. That's correct. All right, let's go a little further. Section 8.2. Now, the first thing your book does is try to show you what we used to call little projects that we do in math. And it shows you the problem without really You have because they both have to be less than 90, so they can add up to 90. Does that make sense? You can go home and contemplate it for an hour. Okay, I hope you have a book or you can look on. Because right here at the top of this page, introducing section 8.2, what they did is they took a triangle. Now that triangle, wasn't calculated in any way. It's just a three-sided figure. And then someone went in there and they cut with scissors. So they have a blue section, a pink section, and a yellow section. Okay? Then they took the whole thing and took the points, which we call the vertex. The vertex of an angle, the plural of vertex is vertices. We're sounding quite funny, fancy here. All right, take the 3 points and line them up together. Just simply put them one next to the other, and you get a straight line. And it doesn't matter what size the triangle is. It doesn't matter what shape it is. It doesn't matter where you cut it. You will always get the 3 angles of a triangle adding up to a straight line. So you begin to think this must be a law of the universe. Who would have guessed that, right? Well, it is. So that, if you have some time you want to play around, just draw any triangle at home and cut the thing up into 3 things and line them up and you see, it's a straight line. All right, therefore, this is a geometry theorem. Geometry theorem is something that if you were in the geometry class, they would actually prove it. Well, we're not going to prove it, we're just going to accept it. If you have a triangle of any shape at all, A, B, and C are the 3 angles, then it's true that the sum of the angles is 180. So angle A plus angle B plus angle C equals 180 degrees. Now, because of that, they can give you silly little problems like this. They start out with the right triangle, so that this is a right angle. And they say, oh, well, this is A, and this is 38 degrees. They'll say, get angle A. Well, for that, you have to know that the right angle is 90 degrees. Very simple idea. So you say, well, if I add up A plus 90 plus 38, I have to get 180 according to this. If you add up the 3 angles, you get 180. Well, 90 plus 38 is 128. And now, if you want to figure out what that is, you say, what number do I add to 128 to get 180? Well, let's subtract the 128 from the 180, and we'll find out. $52 degrees. So A has to be 52. So in other words, with a right triangle, all you need to know is one angle, and you automatically know the other. And then sometimes they do a little tricky thing here. They take 3 lines, form a triangle, and they give you this inside one there. This one they call B, this one they call A, but they give you this outside one, 130. This is called an exterior angle because it's outside the triangle. These in here are all called interior angles because they're inside. Okay, so now you have to do a little thinking about this. Whatever A is, when you add it to the big angle right here, you have to get 180 because you get a straight line. So once again, 130 subtracted from 180 gives you 50 degrees. So that's what A is. Now, because you know 50 and you know 43, you can figure out what B is. So you just chase these things down, that's all it is. The sum of the three has to be 180. So B plus 43 plus 50 is 180. And again, adding them together. And you can find B simply by subtracting 93 from 180. 87 degrees. So it's called playing around with angles. Now, triangles are really quite important in many fields. This architecture is basically rectangular. There's nothing but rectangles here. However, it was done back, I think, in the 1940s, maybe late 1940s, they built these buildings. They're in very good shape for being that old. Now you say, well, how come they're so in such good shape? Look at the walls, look how thick they are. Those exterior walls are over a foot thick. So even earthquakes are not going to disturb them too much. But they have built some buildings on this campus, and they have not been built so well. Anyone know the International Student Center across the little ravine there? Over to the other side? There's that building right there as you get across the bridge. That's the International Student Center. And that was what was called 1950s low bid. Low bid means as cheap as you can get it. And they had a few earthquakes, you know, after they built it, and they noticed it was falling down. And the reason was they didn't put any triangles in it. They put rectangles. If you made a rectangle out of 2x4s here, you know, just a box, that's all, just a frame, you push on it, it'll fall down. Make the same thing, but make it a triangle, push on it, nothing happens. It's rigid. It transfers the stress of your pushing down to the ground, it does not collapse. So triangles are used in construction to make buildings safe. Most bridges you'll see have triangles. What they did is they went back to that building. I don't know if has anyone ever been in that building, the International Student Center? It's a strange building. The windows are about that tall, and they only go above at the top of the wall. So there's very little light in it.
Wow.
But if you look closely, if you go to those classrooms, you'll notice that there's this bar of metal that comes from one side up at the top of the wall and goes down to the bottom of the wall over there. And they do that on every single wall. What are they doing? They're putting in triangles. And that's how they corrected the problem. You know, they wanted to stand up, they had to put the triangles in it, so they did it. So triangles are very important. Now there's several ways of categorizing triangles, and we will look at two of them. First of all, you can talk about triangles instead in terms of the types of angles they have. Now, you can have a triangle that has nothing but acute angles in it. Acute angles are angles, of course, that are less than 90. So this, and this, all acute, that's called an acute triangle. Very simple naming process. You can have a right triangle. We've seen several of those already. You have to have a right angle in that one. And the third type you can have is called obtuse, and it looks like this. It's got one obtuse angle. An obtuse angle is greater than 90, but less than 180. So this is greater than 90 degrees, and that gives it the name obtuse. So that has to do with the types of angles that you have in the triangle. You can also talk about types of sides in the triangle. This is the second way of categorizing them. You can basically create a triangle that has three identical sides. And the only way to do that, same length sides, is to create an acute. So this has to be an acute triangle, but the actual name given to this is equilateral. An equilateral simply means three identical sides, all sides equal length. So very often books will put a little tick mark on the side like that, and sides of equal length are all marked with the same tick mark like that. So that's an equilateral. Yes, it is acute. That's right. It fits into both categories. The next one is called isosceles. Now what happens here is two of the sides are equal length, but the third one is not. This would be a different length. And then finally, the last category about sides has no sides of equal length. They're all different length. So you have stuff like this going on. You could have, and this is 1, 2, and 3. These are called scalene. In a nasty name, scalene. But anyway, that's what they are. Okay, now given all of this, we're going to go back 2,500 years now to a time called the Greek era, when a lot of geometry was being done. There was a philosopher, mathematician then called Pythagoras. This is approximately 500 BC. And he formed a society called Pythagoreans. And it was kind of a mystical society, but they did a lot of mathematics. That was one of the very foremost investigations. They investigated math quite a bit. And he came up with a result that really changed mathematics completely. But it also scared the heck out of everybody. And that often happens, you know, new things sometimes are pretty shocking. He said, let's suppose I have a right triangle. This is a right angle in there, and I make the sides equal length. So these two sides are equal length. These two sides which surround the right angle are called legs. This is leg number 1, this is leg number 2. Okay, then I will draw the longer side, and the longer side will be this one here. That comes from a Greek word. It means the longer side. It's called the hypotenuse. That's this one right here. What he showed is that there's a relationship, a numerical relationship between the lengths of the legs and the longer side. And it goes like this. Let's call leg 1 A just to make it simpler. And this is B. And often the hypotenuse is called C. What he discovered was the following. If we square the length of A and we square the length of B and add them together, then you get the square of the length of C. And everyone says, And that sort of has lasted 2,500 years. And as a result, what we know is that if we know, let's say, 2 legs, we can figure out what the hypotenuse is. Or if we know 1 leg and the hypotenuse, we can figure out what the other leg is, and so forth. But there's a catch here, and that is, notice things are squared. It's not A plus B equals C. It's A squared plus B squared equals C squared, which is going to lead to a bit of a problem. With the right numbers, we're going to have to look at square roots. And square roots are not always nice. Sometimes they have to be done on the calculator. Huh? And when a square root is done on the calculator, if it's not a perfect square number, it's going to become what's called irrational. For example, let's talk about squares and square roots. These two ideas are actually opposites of each other. If you take a number like 3 and you make it square, 3 squared, then of course what you get is 9. If you want to go backwards through that process, there's a certain symbol for it. We've seen it before. It's the long division symbol, unfortunately. But there it is. That's called the square root of 9. How can you tell this from long division? There's no divisor. Okay? Which means this is not division, this is square root. The square root of 9, what does it mean? It means I'm looking for the number which I would have to square in order to get 9. Well, of course, that just goes back this way. Because then you can recognize that 9 is 3 squared, so therefore the number I'm looking for is 3. Okay, so we say the square root of 9 is 3. That's how that would be read in terms of English. Well, that's fine. I mean, when you've got a perfect square sitting underneath your square root sign, it's no problem. We can talk about the square root of 100. What number do I multiply by itself twice to get 100? And 121?
No.
Ah, somebody did study that table. Okay. That's the 11 table, right? Now let's see who studied this one.
No.
13. That is 13. 13 squared is 169. Now please note that the square root of a number is not the number. Okay? Sometimes people say square root of 9. Oh, that's 9. No, it's 3. Watch out for notation. Easy to get confused on the test, things like that. Okay. However, if you change one tiny little thing here, like let's say we want the square root of 8.
Irrational?
I'm waiting.
4, 4,
That's the problem, right?
No.
4,
No, it's not 4.
8.
4 squared is 16, isn't it?
Yeah, 4 times 4.
We're looking for the number which when multiplied by itself gives you 8.
So,
Well, I'll
2,
keep you out of the
1.
suspense here.
8.
4 3/4.
1. Is it 1?
2.8. 2.8.
Okay. Notice it's a little bit less than 3, huh? 3 if you square it, if you multiply it by itself, will give you 9. So you expect the square root of 8 to be something just a little bit less, and it is. It differs out here in the 10th position. But the problem is this stuff. That makes this what's called irrational, huh? Meaning that you can't write it as a ratio of two numbers. And it means the decimal version of it goes on forever. It never stops. Well, in order for this relationship to be true for the right triangle, it turns out that depending on the length of the legs, you could get a lot of irrational answers. And when he announced this to the world, this was 500 BC in Greece, They knew about numbers, they did a lot of geometry. An irrational number? No, God would never do that.
No.
That was what they said. God would never make an irrational number. That's the work of the devil. Really. I'm telling you, this is what and they just freaked out. So badly that Pythagoreans were often threatened with death messages. And you think, oh, this is silly. The Pythagorean society went on for well over 500 years, went into the Christian era. And several places in that time, Pythagoreans were killed for talking about irrational numbers.
Wow.
Today, it's no problem. You can punch them up on your calculator in a second. There they are. That's a deadly thing there, folks. There it is. Put it on the board. Don't tell anybody, you can get killed for that, right? And that's how silly it was. Really. And yet, this is all part of history. So, let's do some work here. His original right triangle looked like this. He chose a specific length. He chose this to be 1 and this to be 1. That's a right angle. The question is, how long is that? Well, he said this relationship is true. So let's go ahead and use the relationship and see what happens. I'm going to square 1, add it to the square of 1. And that's got to be c squared. So this gives me 1 plus 1, right? Because 1 squared is 1. And this gives me 2. So c squared is 2. So now I'm looking for the number which, when you multiply by itself, gives you 2. That's an irrational number. And so he figured out what this number was. It's called the square root of 2. And you can punch it on your calculator, 1.414 something, something, something goes on forever, huh? Okay, that's the square root of 2. And that's the one, he said, well, I've made one of the greatest discoveries in mathematics, and I can't tell anyone.
The square root of 2, what is that though?
1.414. That's, we have to abbreviate it. We have to chop it off because it goes on forever.
Yeah.
So this is approximately, put it in your calculator, see?
Yeah.
What happens after the 414? What are the next numbers after?
What did you say?
Yeah, I got a question. I think I pushed out, this is right here, this is right here, that's the right.
It's on top. What you do is push second and then push that.
Oh, the second.
Yeah, and I'll mention that. Thanks for bringing that up. Okay, let me just get that for you so you can see what it is. Actually, this goes on to 2, 1, 3, 5, 6, 2, but it keeps going on. It never stops. And they're such nasty numbers that everyone said they don't really exist. You're just kidding us. Well, obviously they exist. Wouldn't you take a tape measure and measure that thing? Of course it exists. That's a silly thing to say. But it is irrational. He proved it was irrational. Now let's talk about the calculator for a minute, because Aaliyah has a point here that we should talk about. Very often, your square root button is not a button on the calculator. Quiet and talk. I like to throw things. So what you'll get on your calculator is a button that says x squared. Now this is not all calculators. This differs from calculator to calculator. But above it, you'll see that. Okay? So in other words, they're using the same button for two different purposes. If you want x squared, just push it. But if you want that, you have to push second and then x squared. And then you get square root. Now, it's even worse than that, folks, because with some brands of calculators, you push the square root before you put in the number. With some of them, you push the square root after you put in the number. And you've just got to play with your machine to figure that out, because there's no rule about that. So you'll have some homework where you'll have to calculate some square roots on the calculator. It's called getting used to the machine. All right, let's see what can be done with this. Well, first of all, let's look at some triangles, some right triangles, and get some calculations done, and then we'll actually see some problems that can be solved with it. So here they start out with this kind of a right triangle. Here's your right angle. They give you some sides here. They say this side B is equal to 8, this side A is equal to 6, and that's called C. C is almost always reserved for the hypotenuse. All right, so what we know is this, that if we square A and we add it to the square of B, we get the square of C. So that's going to be 6 squared plus 8 squared is equal to C squared. Well, that's 36, and that's 64. Adding the two together, you get 100. Isn't that nice? So what number squared multiplied by itself gives me 100? 10. So C is equal to 10. So this is called a 6, 8, 10 right triangle. It's one of the classic ones that works out really nice because it's perfect square. They're not all about like that, though. Some of the problems are a little bit different. All right, let's look at another classic. Here's another right triangle. This length up here is 12. This one is unknown. This length is 13. Okay, now we keep the same formula going. It's just that we'll be putting actual numbers in for the different letters. Here's the basic formula. And that C has to be the hypotenuse. These two are the legs. So I'm going to take A, which is 12, and square it. Now B is just B, so I call it B squared. And over here I have to square 13, which is 169. This is 144. So now, in order to figure out what b squared is, I simply take the difference between 169 and 144, and that comes out to be a nice number. So b squared is 25. Okay, so I'm looking for the number which, when you multiply it by itself, gives you 25, so that b has to be 5. So given any two of those sides, you can calculate the third as long as you've got a right triangle. All right. Little application problem here. This is on page 477. When Barb swam across a river, the current carried her 300 yards downstream from her starting point. If the river is 400 yards wide, how far is Barb swim? Looks something like this. Here's my approximation of a river. So she starts here. This is Barb swimming. Now, of course, she wants to go across the river, but she doesn't go directly across because there's a current, and the current goes this way, and it brings her down here, downstream a little bit. And that's going to be her end point. Okay, we know that this is 300 yards, and we know the river is 400 yards wide. Question is, what was her actual travel, the distance that she traveled? And there's the right triangle. You got the two legs, 300 and 400, and that's the hypotenuse. You can call it C if you want to. So it's going to be something like this, 300 squared plus 400 squared is equal to C squared. Now those are large numbers, huh? When you square this, you're multiplying it by itself. So you have 300 times 300. Well, it's very easy to do because of all the zeros. Remember, when you multiply powers of 10, it's very easy. So multiply the 3 times the 3 to get 9, and you have 1, 2, 3, 4 zeros, huh? There it is, 90,000. Likewise, this is easy too. So we have 90,000 here. This is going to be 160,000 there. And that's equal to C squared, which gives 250,000. And the question is, what number do I multiply by itself to get 250,000? Well, you have to turn the page to find that, or put it on the calculator. And it turns out that 500 will do just fine. So she actually goes 500 yards instead of 400 yards to cross the river.
What page are you on?
Well, that was on page 477. Okay, let's look at some problems where we actually have to use the calculator. Just to make sure we've got the button pushes correct. By the way, I have to give you a little update to the Pythagorean theorem. Let's write it down again because it's considered one of the most sacred things in mathematics. Mathematicians are never, they're never just accepting of what's been done in the past. They always want to push it into the future. So they look at that and they say, well, that's a very unusual relationship between two numbers. It has to do with squares. I wonder if you could do that with cubes. Well, they tried. Now, they tried that for 2,500 years. Nope. Cubes don't work. How about fourth powers? Fifth powers? Nope. Couldn't find anything. So there was a man, I think Fermat was a Frenchman, maybe 1500s, 1600s. And he was a mathematician. And he kept journals. And in one of the journals, as a side note on the journal, he said, I found an elegant and short proof that this relationship can only be done for the power 2. Unfortunately, he died 3 weeks later. I'm telling you, this is true. This is mathematics, mathematical history. And he never wrote down the proof. So, since the 1500s, mathematicians have been pulling their hair out saying, what was the proof? All right, 10 years ago at Princeton, one of the math professors was given a sabbatical, meaning that you can go off, you get paid, you don't have to do anything. And that happens usually every 7 years, that's why it's called a sabbatical. Anyway, he said, all right, I'm going to prove Fermat's last theorem. Well, he did it. He actually accomplished it. It was verified by other mathematicians in the world. That thick, I'm talking about pages, right? With mathematics that very few mathematicians in the world can understand. Very complicated mathematics. Something that Fermat could never have understood. So he finally did it. Now everyone's happy. You can go tell your parents that story, they'll love it. All right, so here we go. Let's say we want to get the square root of 427.75. Now that's obviously not a perfect square. How are we going to do it? Well, let's say you have one of those calculators where you need to push the square root button before you put the number in. You have to check your own machine to figure this out. So that means you can do something like this. First you'll push second. Second simply means we're going up to the upper description above the button. And then you push probably x squared. Now you may have a square root button. Some calculators do have it. Mine does, but that's a very old one. Okay, so now you've got square root. Then you push in the number, 427.75, and then you push equals. And that should give you the right result, which in this case turns out to be 20.682. And they do that to 3 decimal places. Remember, anytime you take a square root of something that's not a perfect square, it will be irrational. So it'll go on forever. So you've got to chop it off. So they decide to chop it off at 3 decimal places. So that's how you do your button. All right, let us do some ancient Greek mathematics here. This is 8.2.
Oh well. I know.